Our name of our presentation is JavaScript for Science, but for those people that may be watching this in YouTube later or on the live stream, the kinds of things we're going to introduce today and the kinds of ideas that we're going to go over are not specifically just tailored for JavaScript. It's just we happen to have some examples from web development that are exceptionally pertinent. So the title of our talk was JavaScript for Science because we thought that was a really cool name. And my name, as Anna mentioned, is Angelina Fabbro. You can find me as Angelina Magnum on Twitter, which is a great place to ask either me or this person next to me questions. And I work for Mozilla. We are an organization who I'm sure you're all familiar with. We generally try and do good things for the web and for humanity. Things like, bringing smartphone experience to other countries that otherwise don't have it, and also help you protect your data and things like that.
And I'm Bill Mills. I'm a nuclear physicist currently working at TRIUMPH, Canada's National Lab for Nuclear Physics. And before that, I worked on the ATLAS project on the Large Hadron Collider.
All right, so sometimes when people talk about changing the world, you get kind of like this airy-fairy sense, and you come across people who have, a lot of really kind of interesting, idealistic notions, but they aren't terribly grounded in reality a lot of the time. I'm firmly of the belief that, that if everybody does just a little bit, we can actually make really big changes. And what we're going to talk to you guys about today is how you, as industry software professionals, can be helping people in the natural sciences do better science and thus make, larger and more interesting advances for all of humanity. And by the end of the presentation, I want you to come away with the idea that you are absolutely capable of this and have some ideas about how to do it. And working together, we can hopefully make the world a better place. So it's time for some real talk.
So I'd like to start this presentation with a bit of a confession, and that's that a tremendous divide has opened up between the worlds of natural science and software development. And that divide is starting to cost the sciences a tremendous technical debt. Let me see if I can start by contextualizing a little bit of what I mean by something I like to call Moore's Law, CERN style. So the real Moore's Law, of course, says that the number of transistors in an integrated circuit doubles every 18 months or 2 years or what have you. And qualitatively, a similar thing has been going on at CERN with our big detectors over the past little while. So in this chart here, I've got the number of data collecting sensors per flagship experiment at CERN since the early 80s. And in the 80s, we had an experiment called UA1 that had maybe 10,000 data collecting sensors in it. Fast forward to today, and the ATLAS experiment on the Large Hadron Collider has to the order of 100 million channels, 4 orders of magnitude more in just 3 experimental iterations. The scale of our experiments is exploding. And as a result of this, we've had to put a lot of effort into visualizing our data. So for example, any collaboration member at ATLAS would recognize this event as having the fingerprints of the Higgs boson in it, which we helped to discover last year. And yet, despite all the effort that we've put into things like visualizations and how far our hardware has come, in the 5 years that I wrote software for ATLAS, I never received one single code review. In all of the software meetings that I went to every week, words like scalability, portability, reusability, usability at all never entered the conversation. Though we're skyrocketing into the future with our science, we're still coding like we're 5 people in a room in 1970. And you can imagine the tremendous technical debt that builds up from not keeping up with computing best practices. Meanwhile, in nuclear physics, we have this nifty thing. It is a web app called MIDAS, and we use it for real-time monitoring and control of our experiments. One thing that's really cool about MIDAS is that this is a web app whose first version was developed in the mid-90s. Now, web app was not a word in the mid-90s when this was first developed, and yet physicists said, this newfangled internet thing, this is the way to go. This is what we want to use for usability and portability for our experiments. So we built this, we've used it ever since. It works very well for us. And yet, this was built 20 years ago, and in that time, the people in this room have done tremendous, beautiful, brilliant things with web apps and user interface technology, and yet MIDAS remains exactly what it's always been, a giant table dump of the thousands and thousands of numbers that go into one of these experiments. Why haven't we integrated your brilliant ideas? They're so beautiful, they work so well, and yet we're kind of still in the 90s here. This, again, is a massive technical debt that we need to overcome.
Right. So Bill and I, when we were preparing this presentation, we realized that I guess we've known each other now for just over 2 years, like almost 2.5. And we originally became friends because I found out that Bill was working on the ATLAS collaboration. I had all sorts of questions about the Large Hadron Collider and just physics in general, because that's not my domain area. And Bill knew that I was practicing software engineer and I was shipping apps and wanted to know, like, you know, what my thoughts were on programming, because Bill happened to be doing some programming himself, but didn't have as much experience. So we became friends and had a lot of conversations about this. And I'll remember this one day, probably forever, where Bill interrupted what we were talking about. He's like, oh, I gotta go do something on the computer. I'm like, okay. And I kind of did that jerk thing where, like, you look over someone's shoulder and you're like, you really shouldn't be, but I kind of wanted to see, like, what he was coding for Atlas. And so I look over his shoulder and I'm like, oh, okay. Hey, so Bill, is that real? Are you really on line, like, 6,000? Yeah, why? So really, that line is 6,000 out of how many lines in a file? And I don't remember how many lines it was. But, you know, I said to Bill, I'm like, why wouldn't you spread that information or those functions and those things that you're doing across multiple files so it's a lot easier to manage? And this just hadn't occurred to Bill before. This was the first time that had ever come up as a topic, and he explained to me, like, this is just how everybody does things. I was like, okay, so we've been friends for a little while, like, how early is too early to introduce, like, coding conventions into your relationship with someone? Because you know things like semicolon insertion and comma first, like, that ends friendships right there. So I was just, you know, paranoid. But thankfully, Bill and I are both very similar in that we both want to become better programmers and better at the things that we do. And so exchange of knowledge and feedback like that was not an uphill battle for us. And of course, we've been having a conversation about this stuff now for almost 2 years. So really, this is just an example of just, he's obviously an intelligent person, otherwise he wouldn't have gone to work at, you know, CERN and become a physicist and all that. At least I maintain that about him. And so he's obviously capable of learning the things that you and I know. So I think this is really just a case of sometimes you don't know any better. So for a moment, let's actually take a look at a few examples in actual code that's in production in scientific experiments, and let's take a look and see what natural scientists are doing. So this is probably going to be really blurry, and I apologize, because hold on a sec, maybe we can, like, fiddle with this a bit more and make it better.
That's all the fiddling we're going to
That's all the fiddling we're going to get. So what I'll do is I'll describe this and I'll walk you through what we're looking at, because it is a wall of text, and that's sort of on purpose, because there's a lot going on here. Now the first thing is that in this region here, we see that there's a variable called z, not very descriptive, but we also notice there's variables called x and y. Okay, I can probably make the assumption that each of these variables refers to a point in 3-dimensional space. Okay. But there's no comments, so I have no idea actually what this calculates. I don't know what can face thickness is. Furthermore, we've got the magic number of 2.0. We're dividing things by 2.0, and there's no descriptive variable name that we could reuse that would describe, you know, the code a little bit better. But the thing that's most interesting is over here on the right. I mean, this is taken from Sublime Text, which I'm sure a lot of you are familiar with. For those who aren't, on the right here, Sublime Text provides you with a nice little window to show you where your screen of code is in relation to the length of the rest of the file. And the first thing I noticed when I opened this is that there's actually a pattern here. And if there's a pattern that's being repeated, what does that mean? This piece of code was copy and pasted 16 times. So the person that wrote this either did not know that they could make functions, or they didn't understand how to take this information and put it into a function so that they didn't have to copy and paste 16 times. So this next one is actually my favorite of the 3 that I'm going to go over for you. The first thing is that we're on line 13,000 of who knows? And the next thing is that I like that Bill named it longest string ever.c something. Because what's actually going on here is that this is a big concatenated string in C, but on closer inspection you find, what's that? Holy crap, that's JavaScript. Why are you writing JavaScript in a giant concatenated string from C? And also there was HTML too. And so I asked Bill, I was like, Bill, like, why are we doing this? We actually don't know. We still don't know. This is a legacy system that Bill ended up having to work on, and he was like, come over and look at this. And I'm like, oh my gosh. So, you know, and so what's very interesting about this code is that I think that what happened here is somebody was, you know, probably they decided, like, I'm going to write everything to HTML and use some JavaScript. Yeah, okay. But they know C the best. C is the hammer that they have for fixing problems. And probably it's maybe possible that they didn't even write this JavaScript. Maybe they found a snippet somewhere on the internet, or somebody else wrote it, and they probably just pasted it in there. And I'm willing to bet that they probably didn't know how to write JavaScript, because anybody who knows how to write JavaScript and HTML, unless they're doing some sort of experiment in this day and age, does not have it output from a C program. It's a little bit like this, where you're trying to put the square peg in the round hole. You've asked for you've asked for a JavaScript head screwdriver, but you have a hammer that says C, and essentially you just circumvent the process by doing this. I love this GIF. I've used it like 10 times, but I always find something to apply it to. But that's what it's like. And so the last bit of code is very notable, first of all, because you can see the giant pyramid of doom that's going on here with the code. I'll come back to that in a sec, but my favorite part is, hey, holy crap, there's a comment. Woo, okay, let's see if it tells us anything about the code. Map the data from the JSON P store into the DAC object. I don't know what a DAC object is, so I'm just going to assume it means Dairy Queen. Summing the rates as we move upstream. We're not actually dealing with a stream, so I sort of assume that this person means like as they go through the object and collect values, they sum them up. And that was my assumption, but I don't actually know because there's only one comment. I mean, the next thing is that like it looks like they're checking against array index out of bounds with like a -1 there. This high amount of, like this high degree of nesting is usually very bug prone and error prone because, you miss like one closing brace. I mean, you can mess up your scope and stuff like that if it doesn't throw an error. And I feel like if we spent some time on this, we could probably flatten it out a lot. And guess who wrote this code? That guy right there. Pardon me, excuse me. So the one thing that I want to stress, though, is like we're not showing these code examples to be like, haha, bad scientists, you should feel ashamed of yourself. Because when I was beginning coding, I wrote stuff like this. I found my old Compute 225 and 310 assignments the other day, and I did things like this. But the thing is, from us in the audience, like we have a good giggle at it. It's easy for us with the experience to look at this stuff and say, oh yeah, like I could totally clean that up. Whereas somebody who doesn't have software experience, they just don't know any better. Which actually brings me to my next point, and that's that for people in the natural sciences that are doing this stuff, there's an impetus to write unmaintainable code. So in a lot of situations, people that start in a lab or are starting their PhD do not have anything more than a first year computing course as their experience. A lot of people in this room are probably self-taught, but for those who went to university and took like, intro level computing, you probably know that that first course really only contains control structures and some scope. And then that's it, right? There's only so much that people can absorb at once in one course. So that's not sufficient knowledge and information to go on to write really complicated software, which is what these people do in their job now. And further to that, if you're in a lab, there's often a lot of time pressures. There's a lot of pressure to get your thesis done for your PhD, to have your paper ready for a publication or for a conference. Those similar pressures that we have ourselves in the software industry, like being able to ship a certain version on time. And you guys know as well as I do that when you're under a lot of time pressure, you don't write the best code. So there's also that to consider. The other thing that I want to mention is that a lot of the times people write this code and they think that they're writing single-use code. They think once my PhD is done or once this paper is published, I'll go on to some other institution, I'll go on to something else, and I'll never need to look at this again. But Bill and I have learned in practice that this is often not the case. Sometimes a grad student will start and their supervisor will say, hey, you're trying to study the phenomenon of X. Well, it turns out that Bill Mills wrote some software that calculates, something like X. Here, look at his code and see if it helps you. And then what these people run into is they're looking at another example of bad code that they will probably not understand with no comments. They'll spend a lot of time trying to figure it out. Then they'll extend it with the same bad practices, and thus the cycle continues. But the good news is that not all lab science is the same.
So for the past year now, I've had the great good fortune to work for the Griffin collaboration at Triumph. The Griffin spectrometer is a new next-generation gamma-ray spectroscopy experiment coming online at Triumph next summer, and our physics goals are threefold. First, we would like to investigate the R process, which is how the heaviest elements in the universe get made in supernovae. Second, we would like to investigate fundamental symmetries of nature to cross-check some high-energy experiments, like at CERN. And thirdly, we want to continue Triumph's long-standing tradition of being a world leader in the study of nuclear structure. That's our physics list, but on the computing side of things, I believe that the Griffin experiment is a tremendous opportunity to take a step forward in how we interact with code and how we build user interfaces to interact with our experiments. Because the inadequacies that Angelina pointed out in the way we're developing our software is not just limited to our code, we still also have a lot to learn about UI. So over the past year, I've been trying to bring in ideas from information architecture and web design and use web technologies like JavaScript to build a user interface for Griffin that requires as little domain knowledge as possible for experimenters to use. So I'm going to take you on a very quick tour of Griffin.js right now. It'll be a little demo of my web app, and we'll talk about some elements of it in more detail in a moment. Oh, that's not it, that's MIDAS. Here we are. Here's Griffin.js, and it's composed of a number of different performance targets. The most important one are these skeuomorphic representations of our detectors that preserve context of information as it comes live off the experiment. Another goal for this project was to develop a high-density view for our high-voltage channels so that I can immediately see if something's gone wrong with one of my channels, as opposed to having that information just spread out in an unreadable giant table dump like we had before. Other goals was to produce a data throughput monitor. So right here I can look at how much data is coming off of groups of my sensor nodes and getting pushed up to my main data acquisition computer. DAC stands for data acquisition, not
yeah, it's not Dairy Queen. I learned that later.
And there's also a bunch of control interfaces here, which I'll actually take you through in detail in a moment. But to begin with, let's focus on our skeuomorphic representations of our detector systems.
So what we're looking at here is a detector called Descant. Descant is a 70 sensor neutron detector, and it's about as big as my arm span here. It's a concave kind of bowl thing, and you can imagine it sort of lined with these hexagonal things. It's kind of like a Orby beehive thing. And the thing that we have at the bottom here is a scale that shows from 0 hertz to 1 kilohertz, and these colors represent the firing rate of these channels. And most of them are all a nice warm color, which means they're probably firing at a rate of somewhere between 500 to 800 events per second. But the one thing that you probably notice is all of these are black right here. What's the deal with that? Now, if we were still using a system like MIDAS, a giant table dump, in order to know that something was wrong with this detector, somebody with domain knowledge would have to scan this table manually. You'd think there'd be an automated script, but no. You'd have to scan the table manually and look for zeros. And all those zeros might not necessarily be clustered together. You'd have to pull out all the zeros and make a note of which parts of the detector or which sensors have the zeros. And then you'd have to figure out, based on identifiers, you'd have to actually go into that sort of concave bowl thing with all of these sensors and then sort of map and figure out which ones are functioning. Now, I know that skeuomorphism as a design philosophy comes and goes in front-end web development from day to day or year to year, depending on who's the popular designer at the time. But in the realm of natural sciences that have experiments like this, in particular physics, the skeuomorphic representation of the detector is awesome. It preserves so much contextual information. We know immediately from looking at this that, hey, all the zeros happen to be in this one region, and there's a huge problem. We also know that there's some other ones elsewhere that could be a problem. But we know there's a big problem going on here. And so this skeuomorphism actually is a huge asset for modeling these detectors. One thing that's really interesting about this thing that Bill coded, and I mean, those of you who have more UX experience and UI experience are probably it's kind of ugly, but Bill basically built this is his first web app that he basically built with he would come to me and be like, hey, so how to UX? And I'd be like, okay, we'll provide you some resources, give you some feedback. Or how to JavaScript? I'm like, okay. And one day he came to me and said, okay, I have a bug in my JavaScript. Can you help me? I'm like, I'm on it. Okay. So he's like, I'm having a problem with the sidebar, and I don't know why the length isn't expanding to the full height of my browser window. I'm like, okay, I got this. This is cool. And I right-click on it, and I expect to find DOM elements, but then I don't. It turns out that Bill had done everything at all for the entire project, all in Canvas. Now, this was very interesting to me because I know that I taught Bill the document object model kind of stuff, and I taught him how to use CSS, and I know that he knows these things reasonably well. But it turned out that when Bill got to implementing stuff like this, he didn't know things like CSS sprites and didn't really understand how he would make a hexagonal div. But he did find this thing called Canvas, and he's like, well, I can write exactly the pixels I want to the screen, exactly where I want them. Ultimate control, right? Physicists, turns out, really like that. So he managed to do everything on the website, including implementing the header and the sidebar, all in Canvas, and even implemented his own click handlers and tooltip overlays, and I was just blown away by this because that's so much coding and work. And he didn't use any third-party libraries. He just thought, well, I'll just write the pixels and they'll do what I want. And by and large, that's true. Now, this is a bit serendipitous in a sense because with all the kind of information and the number of elements that Bill has to monitor, it actually turns out that having these as canvas elements rather than a multitude of DOM elements, that would be a lot, is actually going to be more performant overall. So Bill sort of accidentally got himself into the right situation, but you can understand how someone not having the relevant knowledge about what to choose and when, this could have gone sideways. And since that whole conversation and bug and stuff like that, the sidebar is now implemented with CSS and DOM elements and stuff, whereas this stuff here is all still canvas, which makes a lot of sense. So I find that particularly interesting.
So in addition to live representations of our detectors, there's also an inadequacy in these table dumps when it comes to interacting with our experiments beyond just representing them. So in any one of these experiments, we have to define something called an experimental cycle, which is basically a set of steps on what we do to run this experiment. So to understand a simple experimental cycle, what you have is these detectors are all arranged in this big spherical array, and they're looking at one point at the middle of the sphere. And we have what's basically like a movie reel tape that we can move in to the center of the sphere and turn on our radioactive beam and implant a bunch of isotopes on the tape at the middle of the sphere, and then turn on our detectors to observe the radioactive decay of these isotopes. Simple experimental cycle, we set that up, we run it till we run out of money, and that's our experiment. It used to be that each of those steps had some bit pattern associated with it. What you had to do, if you wanted a bunch of those steps together, was take those bit patterns, and them together by hand, yes, and then take the hex representation of that handed bit pattern and write it into some appropriate slot in that MIDAS table dump before. This is terrible. I mean, that is an awful, awful way to interact with your experiment. It demands a lot of domain knowledge, it's labor intensive, and it doesn't take advantage of any, like even basic ideas of interaction design. So what I said to myself is I said, all right, most people on this project know how to use a smartphone. They're familiar with, the basic vocabulary of interacting with things like this. So why not just make a simple drag and drop structure? So I got that right here. I might want to say clear some memory to have some room to write new data. So there it is. I'll move my tape into place, like I said. There we go. Implant some isotope for a while, and then triggers on. That's just like turning my detectors on. There we are, done. That sets up the experimental cycle for Griffin, just using simple, like, smartphone vocabulary for setting these things up. This is a tremendous leap forward in terms of our interaction design just by using some fairly obvious ideas from your field.
Right, so all of you can do science. One of the things I've run into in trying to sort of convey this information to people who are also software developers is I'll talk to them about the idea and they'll be like, yeah, no, I think science is really cool. Maybe they love Star Trek, maybe they love Babylon 5. I love Babylon 5. Maybe, they like sci-fi, maybe they think the idea of the future is cool. I mean, I'm sure there are plenty of people in the audience that feel that way. I get really excited about science. But I've noticed that a lot of people, because they are not scientists by trade like Bill, or they didn't do a PhD, they think that probably they don't have the necessary knowledge to contribute to science. But it turns out that this is patently false. In 2012, I organized the Vancouver chapter of the International Space Apps Challenge, which is an event that NASA puts on in collaboration with a few other organizations. We had about 30 to 50 people, I don't remember the exact number, come and do a hackathon for an entire weekend, and we got some really fantastic results. I had some people come that were like, UI and UX people. We had programmers from the software industry, both front-end and back-end, wide variety of languages. We had people come from computing science at SFU and UBC, and we had a really, really diverse mix of people, so it was awesome, and some really great things were produced. One group in particular, the one that I think won gold for our location, they did a 3D model with real-time data from NASA showing the progression of the aurora borealis. It was really cool. And they were talking to me, and they said, Saturday night during the hackathon when we went home, we had some friends over, and they were really excited. They were like, they really wanted to know what we were doing at this hackathon, and when we told them, they thought it was really cool. And I asked them, well, what do your friends do? Oh, well, they're in computing as well. I was like, well, why didn't they come to the hackathon? And the answer was simply that they thought that because they weren't in physics or they weren't, somebody studying space, that they wouldn't have the necessary skills to solve those challenges, or that their skills wouldn't be an asset. And from the results we got from this, it's this patently false. There's plenty of ways to contribute, and there's plenty of ideas out there that are looking for someone to help them solve them that, can come from the software industry. So on the other side of things, there's this interesting mentality in some of the sciences where people will sort of be very insular in their labs or on their project. And it makes a little bit of sense because often people are trying to be the first to publish on a particular topic, and so they don't necessarily want to be totally open until they publish their paper. Science should be open, but people kind of get a little insular because they want to get the scoop kind of thing. And, I think it leaves them feeling like this, really, right? I mean, software is not their particular, domain of expertise. Bill told me a story about how when he was writing code, he had many nights like this because he was given a proprietary data format that he had to unpack, and nobody on the collaboration knew how to deal with that data. But it was his responsibility, and he spent, can I say how long?
4 months.
4 months trying to work with this because he didn't know anybody in the software industry that he could ask, what's a good tool for this, how to deal with this. And nobody on the collaboration knew how to help or even cared to help because they were busy with their own thing. And so as a software engineer, I just want to say to scientists out there that may see this presentation, you don't have to do everything yourself. And if there's something that you're concerned about that's sensitive information, we are all familiar with those ideas in software, and I'm pretty sure that we can all be quiet about what you're working on. You know what I mean? Like that can be negotiated. It shouldn't be an impediment. And so really, science should be a collaboration. I feel like if you're not, if you're not accepting help from the domain that you don't have experience in, but you're trying to participate in that domain, you're doing yourself a disservice and the science a disservice. The science should really be a collaboration, so you should come work with us, software engineers. So really the question ends up being, how do we adapt our culture and what kind of things can we introduce so that scientists in the natural sciences and people in software engineering or computing science can play nice together?
The answer to cultural adaptation is the same in this case as it is in almost every case involving humans, and that's that people adapt their behavior when they see good examples of how to do things right. The most crucial thing that programmers can do to help the natural sciences is to make connections with scientists in whatever your field of interest is and start reviewing their code. Criticize them, set a good example for them about how to do things right, because many of them would love to learn from you if only they have the opportunity. In concrete terms, the things we desperately need is, first and foremost, getting scientists to put their code out there, make it open source and available to everyone. This serves the crucial practical element, is that how are you supposed to criticize code that you can't see? So we desperately need it to be up on GitHub so that we can share it and review it among each other. That's one thing about Griffin, is we recently put all our code up on GitHub, so it's available for everyone to come and have a look at and criticize if you want. Once that goal is achieved, code reviews are the most crucial thing you could do for the natural sciences. And these don't have to be long, involved processes. I wanted to show you those code samples at the beginning of this presentation, as well as my UI and UX decisions, to drive home the point that a lot of the mistakes being made are not very complicated. In fact, they're very amateur. They're the sort of mistakes that anyone in this room could point out after like 2 minutes of looking at this code. In so doing, you could influence the development of a young scientist to say, hey, I guess I should factor things out into functions and do this properly for the rest of their careers. That small contribution of an hour discussion early can ripple outwards forever, for a lifetime. Beyond code reviews and sort of the nuts and bolts stuff like this, obviously for my little demo of Griffin.js, we also need plenty of advice on UI design and strategy. I'm trying my best to pull in good ideas I've seen on the internet, but most of the time, working with web design for someone trained as a physicist feels kind of like this. I don't really know what I'm doing, and I like the story Angelina told, I find this cool canvas thing that I can do anything I want in, doesn't argue with me or give me any problems like the box model does, and so I can just push everything onto that and make it do what I want. But really, I mean, come on, that's terrible, right? That's not the best solution for this. Early in my project, if I had had this short discussion with a software developer, someone could have said, hey, there's a lot of other solutions for this. Consider these frameworks, consider these solutions. And it would have changed the whole course of this project. For those of you more interested in the hardware end of things, there's tons of options as well. One thing I didn't mention about Griffin is that we will be writing 200 terabytes of data to disk every week in this experiment. And we'd like to analyze that data in 1 day. This is not an insurmountable challenge, but it's been complicated enough that we've had a number of meetings at Triumph arguing about what hardware to buy and how to assemble a system to do this. I bet there's some people in this room that could whip up an idea in a couple minutes. It's not that tough or that complicated.
So, as a software developer speaking to scientists, there's some particular, it's like a particular paradigm shift that kind of needs to happen as as I've been explaining, pardon me. Part of that is obviously don't be afraid to import domain experts. That's really important. But the one thing that Bill talked about is get your code in the open, and I want to elaborate a little bit more on that. So one of the things that I've noticed about a lot of these papers in all sorts of fields, whether it be in computational neuroscience, whether it be in physics, whether it be in ecology, people will publish papers and they'll say, okay, I have some math and I proved it with some software, and then they've got this awesome paper. And that's great. And your paper's there explaining your methods, and that's all open, but where's the code? The code is never released. It's never put somewhere. So if someone wants to verify those scientific results, they have to look at that paper and come up with their own implementation. There's no way for them to go back and look at the code that someone used to create that paper, to vet it, to peer review it. And that to me does not really sound like it's in the spirit of openness. All that code, you can keep everything you want a secret till you're ready to publish. But when you publish, throw that code up there too and say, in your paper, here's where you find the code, because it's either going to help benefit the advancement of some other experiment, or someone's going to come along and try and reproduce it or work with your code and say hey, you were really right, or maybe you were really wrong. So having that code in the open is really, really important part of the scientific process, and it's just not happening at this point. So, the obvious one is bring in software developers and computing scientists, and preferably bring them in as early as possible, because a 20, 40-minute discussion about how you're going to design your program's architecture early on sows the seeds for better practices early. But if you encounter a scientist or a lab, or you are a scientist or a lab that has a monolithic, bit of legacy code that you're forced to work with, still bring software people on, because in the industry, sometimes we're thrust into managing legacy code. There are people out there that have experience dealing with stuff like that and can tell you some strategies for the easiest low-hanging fruit to make things more manageable, as an example. And just be okay with the fact that you write crap code sometimes. Sometimes you know what the goal is, right? Like this kitten. You want the milk, right? You know that your goal is to write a program, but you kind of dive right in. And you don't really know what you're doing. So in the process of trying to figure things out, you make a whole huge mess, right? And that's how this code ends up. And I just want to watch this again, because I just love this every time. Look at him go, oh my God. Anyway, but it does seem like that. You think you know what the goal is, and you think that you are going in the right direction. You dive right in, you make a mess. And the thing is, I've done that before too, but we want to just be honest with ourselves that we don't necessarily write awesome code all the time, and to come back and review that stuff. But a way to avoid writing terrible code, and this is a particular philosophy that I think would be really, really well, or do really well for the scientists to adopt. So a lot of people in the room are probably already familiar with test-driven development or behavior-driven development, but for those at home and scientists who may watch this, those are essentially the philosophy that when you're going to construct a piece of software, before you start writing the code that does what you want it to do, you construct a series or a suite of tests, and then what you do is you write your program to meet the criteria in those tests. And that actually has sort of a twofold effect here. One, if you give that specification, that list of tests to someone who's a fledgling programmer, you're essentially giving them a laundry list of the features that you need to ideally have a complete or a functioning program. And so that's actually really good, because someone who doesn't maybe have a lot of experience designing something big, they can focus on one sort of module or unit at a time. And as I mentioned, module right there, it sort of forces you, by necessity when you're doing this practice a lot of the time, to write modular code, which in my experience ends up being a lot more maintainable later down the line.
So the technical deficits that I pointed out today are not limited just to physics. Physics is what I know about, so I talked about it a lot. But before I came here, I spoke to scientists in many different fields, and I asked them, what would you do with a computing professional on your team? And they told me all kinds of stories and different ideas, but the most interesting story that I want to relate to you came from an ecologist. And the ecologist said to me, Bill, the best thing that a software developer could do for me today would be to just sit down with me and have a conversation, because I don't even know what's possible, what could be done. Fields in natural science and software development have diverged so far and there's so little dialogue between them that we just don't even know what we can achieve if we work together. There are some tremendous opportunities out there to solve problems you've seen today and other problems in all different fields of science that you're interested in. All that's required is for you to try to make a connection with scientists in the field that you care about and start a conversation with them.
So when I was planning to come here to LXJS, I'd been talking with Bill for a while, and So part of my job at Mozilla, and before I was at Mozilla, I was giving talks on things like web components, and I did like CSS a couple weeks ago at CSS and so I've got all this experience doing talks, and for a while I'd had this idea percolating that I really wanted to give this talk, because all this stuff with Bill and I had culminated. And so I was really glad that LXJS was super receptive to the idea of this talk, and both of us doing kind of like a joint talk, which is not something that you see terribly often at conferences. But the most notable thing about LXJS, I think it turns out, is that if you go look at the wall of sponsors, I think it's got to be over there. It's tiny for you guys sitting in the audience, but you'll notice that Triumph is up there. That is Canada's National Lab for Physics, and as far as Bill and I know, this is the first time that an industry professional conference on some computing language has been sponsored by academia. They care enough about this idea that we should be working together, that they decided to put their money where their mouth is and sponsor this conference. And that's pretty freaking cool. That hasn't happened before. And so we think that that's really showing that there are steps being taken in the right direction. So hey, here's some dudes, some of them you may know. There's like Brian LaRue up there and Remy Sharp and stuff like that. So while we were preparing this presentation, it turned out that a bunch of these people were flown to CERN, and CERN had them come re-implement the original line browser to preserve a little bit of internet history. And what's notable about this, and why we decided to include it in the presentation, is this is an example of CERN taking domain experts and bringing them on board to solve a problem. Now, they didn't necessarily work on Atlas and the Large Hadron Collider, and they weren't necessarily there for an experiment, but as far as Bill and I know, like, CERN doesn't normally do that. But CERN decided for this project, like, hey, we're going to have some domain experts come in and work on this with us. And we thought, like, wow, that's actually pretty progressive too. That's not necessarily something that we'd seen before. So this website, please go to it, please tweet it. What you will find there is a forum, because what Bill and I are working on, and it's going to launch in Q1, is this website called interdisciplinaryprogramming.com. And what we're going to do there is we're basically going to create a sort of matchmaking service for scientists and labs who would like to find software professionals to help them, and for software professionals who want to express, like, hey, I'm interested in biology, hey, I'm interested in cognitive neuroscience, hey, I want to know more about physics, so that you can find a good fit. And if you have spare resources and time, I implore you to contribute to the sciences, because that sort of stuff benefits all of us in the long run. So the thing that's there right now is a forum. You're not signing up for a mailing list. We would never do that to you. It's just a forum that basically gets, like, your email, whether you're a developer or a scientist, and then we will email you once when the project launches, and then we're totally going to delete everything, because we would never do anything with your data. So please tweet it, please tell your friends, especially pass it on to people in the academic sciences that are not necessarily here today. This video will come out pretty soon, so you can do that as well. And really, we just hope that we've inspired some interest in you, or made you feel like you can be a part of the scientific process. So thanks, LXJS. Thanks for having us.
Thanks, everyone.